We have now seen the local structure of the 16-cell honeycomb. 24 edges, 96 triangular faces, 96 tetrahedral ridges, and 24 16 cells, meeting at every vertex. But we began this chapter with a different question. In 3 dimensions, close-packed space can be understood in terms of 4 special directions. So what happens in 4 dimensions? How many directions are needed to organize the corresponding structure? Let us first return to 3 dimensions. Consider the familiar cuboctahedral picture of the face-centered cubic lattice. A cuboctahedron has 8 triangular faces. These triangles occur in 4 pairs of opposite faces. Each opposite pair defines an axis. So we obtain 4 directions. These are the 4 tetrahedral directions associated with the body diagonals of a cube. They are the directions along which the close-packed layers can be viewed as being stacked. This is the geometric picture behind the classical close-packing arrangement. Now let us make the same kind of observation in 4 dimensions. Our 4-dimensional analog is the 24 cell. The 24 cell has 24 vertices, but its facets are also important. It has 24 octahedral facets, and these facets occur in opposite pairs. So pair the facets and typodally. 24 becomes 12. Each pair defines one axis. Therefore, the natural 4-dimensional count is 12 directions. This is the first geometric reason that 12 appears. But there is an even more direct way to see it. Look at the D4 roots. Every root has the form plus or minus 1, plus or minus 1, 0, 0, with the positions of the 2 non-zero coordinates chosen in all possible ways. First, choose which 2 of the 4 coordinates are non-zero. There are 4, choose 2, equals 6 choices. For each choice, there are 4 independent sign patterns: plus plus, plus minus, minus, plus, minus, minus. Therefore, 6 times 4 equals 24, exactly 24 roots. These are the 24 nearest neighbors of a D4 lattice point. But a vector and its negative define the same unoriented direction. So, 24 divided by 2 equals 12. Thus, the 12 directions are precisely the 12 antipodal pairs of D4 roots. We can write them explicitly as 6 coordinate pairs, each with 2 sign patterns: 1, 2 plus, 1, 2 minus, 1, 3 plus, 1, 3 minus, 1, 4 plus, 1, 4 minus, 2, 3 plus, 2, 3 minus, 2, 4 plus, 2, 4 minus, and 3, 4 plus, 3, 4 minus. For example, the 1, 2 directions correspond to the vector 1, 1, 0, 0, and the vector 1, negative 1, 0, 0, with their negatives representing the same 2 unoriented axes. So the complete set contains 12 axes. And now we can distinguish 2 different answers that appeared earlier in our investigation. The regular 4 simplex gives 5 simplex directions. The D4 lattice gives 12 lattice directions. Both statements are correct, but they answer different questions. The 5 directions are the normals to the 5 tetrahedral facets of the regular 4 simplex. The 12 directions are the axes defined by the antipodal pairs of D4 roots. Our question concerns the lattice and its families of parallel hyperplanes. For that question, 12 is the relevant number, and this is exactly analogous to the 4 directions of the FCC lattice. In 3 dimensions, the close-packed planes come in 4 opposite pairs of directions. In 4 dimensions, the D4 lattice has 24 closest-packed hyperplane families, grouped into 12 opposite pairs. Each pair corresponds to 1 root direction. So we have finally found the direct 4-dimensional analog we were looking for. F on IC, 4 directions, becomes D4, 12 directions. And there is an important structural property. Each of these 12 directions defines a family of parallel 3-dimensional hyperplanes. Take one normal vector. All hyperplanes perpendicular to it form one family. Then take another root direction. It gives another family. continue through all 12 directions. We obtain 12 families of parallel three-dimensional hyperplanes. These are not arbitrary choices. They are precisely the hyperplane directions associated with the D4 root system. And remarkably, the 12 directions are all equivalent under the symmetry of D4. The Weyl group acts transitively on them. So there is no preferred direction among the 12. Each is another view of exactly the same geometry. We can summarize the discovery. 24 roots, becoming 12 antipodal pairs, becoming 12 lattice directions, becoming 12 families of parallel three-dimensional hyperplanes. This is the answer to our original directional question. But now, a much deeper question appears. What does one of these hyperplane families actually contain? If we choose one of the 12 directions and look at the D4 roots lying inside the corresponding hyperplane, what structure do they form? The answer is surprisingly simple. Each hyperplane contains exactly 6 of the 24 D4 roots, and those 6 roots form a complete three-dimensional root system. This means that each of our 12 four-dimensional directions carries its own embedded three-dimensional structure. In the next scene, we will examine those 12 directions one by one and see exactly how the D4 roots organize themselves inside each hyperplane. We have now identified the 12 special directions of the D4 structure. Each direction defines a family of parallel three-dimensional hyperplanes in four-dimensional space. But what does one of these hyperplanes actually contain? To answer that, we can choose just one direction. The symmetry of D4 tells us that every other direction will behave in the same way. So let us choose the hyperplane perpendicular to one of the D4 roots. For example, take the normal direction. 1, 1, 0, 0. The corresponding hyperplane through the origin is x plus y equals 0. Now bring all 24 D4 roots into view. Our question is simple. Which of these roots lie inside this hyperplane? A root lies in the hyperplane precisely when it is orthogonal to the normal. For our chosen normal, that condition is the first coordinate plus the second coordinate equals 0. So we examine the 24 roots one by one. Most of them disappear. Only 6 remain. We have found 6 D4 roots lie in the hyperplane. And this is not special to our chosen example. Every one of the 12 hyperplane directions contains exactly 6 D4 roots. So the relationship is 12 hyperplanes times 6 roots per hyperplane. But now something even more interesting happens. Connect these 6 roots. They form 3 opposite pairs. So geometrically we have 6 roots equals 3 opposite pairs. Each pair gives one coordinate direction inside the three-dimensional hyperplane, and the 3 directions are mutually perpendicular. Thus, the 6 roots form the root system of A1 plus A1 plus A1. This is an important distinction. The 6 roots do not form an A3 root system. They do not form the full root system of an A2 or another larger three-dimensional system. Instead, they consist of 3 independent copies of the simplest rank 1 root system. Visually, think of 3 perpendicular axes. Along each axis are 2 opposite roots. So the 6 roots look like plus or minus E1, plus or minus E2, plus or minus E3, after an appropriate choice of coordinates inside the hyperplane. The geometry is therefore extremely simple. 3 perpendicular directions, 6 shortest roots. But there is a subtle point. The entire lattice contained in the hyperplane is larger than these 6 roots. The 6 roots are only its shortest vectors. Additional lattice points occur at larger norms. Those additional points complete the three-dimensional lattice structure. And this is where the familiar cuboctahedron returns. If we look at the Voronoi cell of the lattice inside this hyperplane, the result is a cuboctahedron. So the cuboctahedron has not disappeared. It has simply changed status. The 6 D4 roots give it 6 nearest lattice directions. The additional lattice vectors supply the remaining vertices needed to complete the caboctahedron. This is a beautiful connection between the 3-dimensional and 4-dimensional pictures. In 3 dimensions, we began with the caboctahedron and found 4 special directions. In 4 dimensions, we begin with the D4 lattice and find 12 special hyperplane directions. Then, inside each hyperplane, a 3-dimensional lattice appears. Its shortest D4 vectors form 3 perpendicular pairs, and the complete Voronoi geometry becomes a caboctahedron. So the structure can be summarized as D4 in 4 dimensions, 12 symmetric hyperplane directions, 6 D4 roots inside each hyperplane, A1 plus A1 plus A1, a complete 3-dimensional lattice, a cuboctahedral Voronoi cell. And because the D4 symmetry acts transitively on the 12 directions, what we have discovered in one hyperplane happens in all 12. There are 12 equivalent 3-dimensional hyperplane families. Each contains 6 shortest D4 roots. Each contains a corresponding 3-dimensional lattice, and each reveals the same underlying close-packed geometry. This is the 4-dimensional analog of the 4 equivalent close-packed planes we encountered at the beginning of the chapter. But now, the structure is much richer. We have not merely found 12 directions. We have found 12 3-dimensional worlds embedded inside 4-dimensional space, all equivalent under the symmetry of D4. And this gives us the bridge to the next question. If each hyperplane contains its own 3-dimensional lattice, how are these 12 families arranged relative to one another? What happens when 2 of them intersect? And how does their intersection reproduce the lower dimensional structures we already know? That is where the geometry becomes truly interconnected. We have discovered 12 special directions in the D4 lattice. Each direction defines a 3-dimensional hyperplane through the origin. And inside each of these hyperplanes, something remarkable happens. A familiar 3-dimensional lattice appears, a simple cubic lattice. So our 4-dimensional structure can be viewed in 12 different ways, each one revealing a 3-dimensional cubic world embedded inside the D4 lattice. Let us see how this works. Choose one of the 12 root directions. For example, the direction 1 over root 2 times 1, 1, 0, 0. The hyperplane perpendicular to this vector is en dot x equals 0, or simply x1 plus x2 equals 0. This is a 3-dimensional subspace inside 4-dimensional space. Now choose 3 mutually perpendicular unit vectors lying inside this hyperplane. These 3 vectors become the coordinate axes of our embedded 3-dimensional space. Call them u1, u2, u3. Together with the normal direction toan, they form an orthonormal basis of all 4-dimensional space. So we have transformed our coordinates into a new coordinate frame, u1, u2, u3, and n. In this new frame, the 4th coordinate measures distance along the normal direction. The first 3 coordinates describe everything inside the hyperplane, and the lattice points lying in the hyperplane form a simple cubic lattice. This is the key discovery. The D4 lattice is not merely one 4-dimensional arrangement. It contains families of embedded 3-dimensional cubic lattices, and there are 12 such families. Why 12? Because the 12 hyperplane directions are the 12 antipodal pairs of D4 roots. Each pair, r and negative r, defines the same hyperplane. Therefore, the 24 roots produce 24, divided by 2 equals 12 distinct directions. Now we can construct a rotation for each one. The recipe is simple. Choose a normalized root u1. Choose 3 orthonormal vectors spanning its perpendicular space. Then assemble them into a 4x4 matrix. Because these 4 vectors form an orthonormal basis, R transpose R equals the identity. And with the orientation chosen appropriately, the determinant of R equals +1. So each R is a proper rotation. The purpose of the rotation is straightforward. It takes our selected hyperplane and aligns it with an ordinary coordinate hyperplane. The 4th coordinate becomes the direction normal to the hyperplane. The remaining 3 coordinates describe the embedded cubic lattice. For our example, the rotation aligns this direction with one of the coordinate axes. The hyperplane x1 plus x2 equals 0 then becomes an ordinary coordinate slice in the rotated frame. What looked complicated in the original 4-dimensional coordinates becomes simple cubic geometry. And now we can repeat the construction. Choose the next root direction. Construct its perpendicular hyperplane. Choose 3 orthonormal basis vectors. Build another rotation. Then repeat. There are 12 directions. Therefore, there are 12 corresponding rotations. R1, R2, and so on through R12. All 12 satisfy the same basic requirements. Each R transpose R equals the identity, and each determinant equals +1. And here something especially beautiful happens. These 12 embedded cubic lattices are not independent. They overlap. 2 different hyperplane families can intersect in a lower dimensional subspace. 3-dimensional cubic structures meet one another along shared lower dimensional structures. And the complete pattern of these intersections is highly symmetric. In fact, the intersection structure reproduces the incidence structure of the 24 cell. So the 24 cell appears again. First, we encountered it as the vertex figure of the 16-cell honeycomb. Then, we encountered its 24 vertices as the D4 roots. Now we see it encoded in the way the 12 embedded cubic lattices intersect. The same object is revealing itself from another direction. There is an even cleaner way to record all these relationships. Instead of writing 12 separate rotation matrices, we can construct an incidence matrix. Think of 12 rows. Each row represents one hyperplane. Now think of 24 columns. Each column represents one D4 root. Put a 1 in the matrix whenever a root lies in the corresponding hyperplane. In other words, the entry is 1 exactly when n.r equals 0. Otherwise, the entry is 0. The result is a 12 by 24 incidence matrix. This matrix gives us a complete combinatorial map of the 12 hyperplanes and the 24 roots. The 12 rows correspond to the 6 coordinate pairs 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, with the 2 sign choices for each pair. For example, x1 plus x, 2 equals 0, and x1 minus x, 2 equals 0, give 2 different hyperplane directions. Likewise, for every other coordinate pair. The complete incidence calculation gives a particularly elegant consistency check. Each hyperplane has the expected number of incident roots. Each root occurs in the same number of hyperplanes, and the total number of incidences is 72. This regularity is exactly what we should expect from the exceptional symmetry of D4. So we can now see the structure at 3 levels. At the first level, 24 D4 roots. At the second, 12 root directions and hyperplane families. And at the third, 12 embedded 3-dimensional cubic lattices. These are not 12 unrelated constructions. They are 12 different 3-dimensional views of the same 4-dimensional lattice. And the rotations give us the coordinate transformations that make each view explicit. This is perhaps the most important geometric lesson of the scene. A complicated 4-dimensional arrangement can sometimes become understandable by choosing the right 3-dimensional slice, and D4 gives us 12 equally natural choices. 12 directions, 12 hyperplane families, 12 embedded cubic lattices. 12 coordinate frames, all connected by the symmetry of the same four-dimensional lattice. But now there is one final question. If these 12 cubic lattices overlap so systematically, can we describe all of their intersections at once? The incidence matrix gives us the combinatorial answer. In the next scene, we will turn that matrix into a geometric picture and uncover the complete network formed by the 12 embedded lattices. We have now seen the 12 three-dimensional cubic lattices embedded inside the D4 lattice. Each one came from a different root direction. Each direction gave us a hyperplane, and each hyperplane contained its own three-dimensional lattice. But we have 12 such structures. How can we keep track of all of them at once? The answer is to replace the geometry with a table, a simple matrix, an incidence matrix. Start with our 24 D4 roots, arrange them as 24 columns. Then take our 12 hyperplane directions, arrange them as 12 rows. We now have a 12 by 24 matrix. Each entry asks one simple question. Does this root lie inside this hyperplane? If the answer is yes, place a 1. If the answer is no, place a 0. The geometry has become a pattern of zeros and ones. But this simple table contains a remarkable amount of information. Look at one row. It represents one hyperplane. How many roots lie inside it? Exactly 6. So every row contains 6 ones. The 6 roots we discovered in the previous scene are now represented by 6 entries in a single row. Now look at one column. It represents one D4 root. How many of the 12 hyperplanes contain that root? Exactly 3. So every column contains 3 ones. This gives us a beautiful symmetry. Row sum equals 6, while column sum equals 3. And because there are 12 rows, 12 times 6 equals 72. Because there are 24 columns, 24 times 3 equals 72. The two calculations agree. We have therefore counted exactly the same set of incidences in 2 different ways. 12 times 6 equals 24 times 3 equals 72. This is more than a numerical coincidence. It is a consistency check on the entire construction. The 12 hyperplanes and the 24 roots fit together with perfect regularity. Now let us look at the matrix itself. At first it appears to be just a collection of zeros and ones, but patterns begin to emerge. Rows corresponding to related root directions have related patterns of entries. Columns corresponding to opposite roots have matching incidence behavior. The symmetry of the D4 root system has been translated into the symmetry of the matrix. In other words, geometric symmetry becomes combinatorial symmetry. This is one of the powerful ideas behind incidence geometry. We do not need to see all 4 dimensions simultaneously. Instead, we record which objects belong to which other objects. The matrix becomes a kind of blueprint. It tells us which roots belong to which hyperplanes. And from those relationships, we can reconstruct the underlying geometry. Now, let us connect this matrix back to the 24 cell. The 24 roots are the 24 vertices of the 24 cell. The 12 hyperplane directions organize those vertices into 12 symmetric families. So the incidence matrix is also recording part of the incidence structure of the 24 cell. The same 24 cell that appeared earlier as the vertex figure of the 16 cell honeycomb is appearing again. But now we are seeing it through a completely different language. First, we saw it geometrically, then through its vertices, now through a matrix. And there is another remarkable connection. Take 2 non-antipodal D4 roots, add them. The result is another vector in the lattice, and in the appropriate cases, it lands on another 24-cell vertex. If the two roots are exact opposites, their sum is 0. Otherwise, in the right cases, the sum is another vertex of the 24-cell. So even addition of roots reproduces the 24-cell structure. The roots are therefore not merely a collection of nearest neighbors. They interact algebraically in a way that generates more of the same geometry. We can now see several layers of the construction at once. At the bottom is the D4 lattice. Its shortest vectors give us 24 roots. Pairing opposite roots gives 12 directions. Those directions define 12 hyperplane families. Each hyperplane contains 6 roots, and all of those relationships are encoded by a 12 by 24 incidence matrix. The matrix therefore provides a compact description of a surprisingly complicated four-dimensional geometry. But there is one more step. We have been looking at the lattice from the viewpoint of its roots and its hyperplanes. We have not yet returned to the 16-cell honeycomb itself. The honeycomb has its own incidence structure, 24 cells around every vertex, 96 tetrahedral ridges, and 96 triangular faces. How does the 12 by 24 root hyperplane structure connect to that four-dimensional honeycomb? The answer is that these are not separate stories. They are different layers of the same D4 geometry. The roots determine the local directions. The directions determine the hyperplanes. The hyperplanes reveal embedded cubic lattices. And the same root geometry organizes the 16-cell honeycomb. So our investigation has come full circle. We began with the D4 lattice. We discovered its 24 nearest neighbors. We found 12 directions. We sliced the lattice into 12 families of three-dimensional hyperplanes. And now we have encoded all those relationships in a single matrix. The geometry has become algebra, and the algebra points us back to the geometry. In the final scene, we will step back and assemble all of these pieces into one picture. D4, the 24-cell, 12 directions, embedded cubic lattices, and the 16-cell honeycomb. What looked at first like a collection of unrelated four-dimensional objects is actually one highly organized structure. And that structure is the geometry hidden inside D4. We began with a simple question. How can the geometry of four-dimensional space be understood through the D4 lattice? We have followed that question through several layers of structure. Now it is time to step back and see the whole picture. At the center is the D4 lattice. Its shortest non-zero vectors are the 24 roots. These are the 24 nearest neighbors of every lattice point. And those 24 points form a familiar four-dimensional polytope, the 24-cell. The 24-cell is therefore not an object that we have artificially placed into the construction. It emerges directly from the local geometry of D4. Now pair every root with its opposite. A root and its negative define the same unoriented direction. So the 24 roots become 12 directions. These 12 directions are the four-dimensional analog of the special packing directions that appear in the three-dimensional FCC picture. Each direction defines a family of parallel three-dimensional hyperplanes. So our 12 directions become 12 hyperplane families. Now choose one of these hyperplanes. Inside it, we find exactly 6 D4 roots. Those 6 roots occur as 3 opposite pairs. They form 3 mutually perpendicular directions. So the local root system is A1 plus A1 plus A1. But those 6 roots are only the shortest vectors. The complete lattice contained in the hyperplane is larger. And when we include those additional lattice points, the familiar three-dimensional close-packed geometry appears. Its Voronoi cell is a cuboxtahedron. So a three-dimensional lattice is embedded naturally inside the four-dimensional D4 lattice, And because there are 12 equivalent directions, there are 12 such hyperplane families. 12 embedded three-dimensional views of the same four-dimensional lattice. Now we can encode all these relationships algebraically. Take the 12 hyperplanes. Take the 24 roots. Create a 12 by 24 incidence matrix. A 1 means that a root lies in a hyperplane. A 0 means that it does not. Every row contains 6 ones. Every column contains 3. Therefore, 12 times 6 equals 24 times. 3 equals 72. The geometry has become a combinatorial pattern, and the pattern is perfectly regular. But there is another structure surrounding all of this. The 24 cell is the vertex figure of the 16-cell honeycomb. At every vertex of the honeycomb, 24 16 cells meet. The local incidence structure contains 96 tetrahedral ridges and 96 triangular faces, so the same D4 geometry appears simultaneously as the lattice, the 24 cell, the 12 directions, the hyperplane families, the embedded three-dimensional lattices, and the 16-cell honeycomb. These are not separate constructions. They are different faces of one structure. Now step back even farther. We can summarize the entire geometry as a chain. D4, 24 roots, the 24 cell, 12 directions, 12 hyperplane families, 12 embedded three-dimensional lattices, a 12 by 24 incidence matrix, and surrounding all of it, the 16-cell honeycomb. There is one final point that is important. The 12 directions do not mean that the honeycomb is constructed by independently translating a 24 cell along 12 unrelated axes. The centers of the 24 cells occupy the full D4 lattice. The 12 root directions describe the natural families of parallel layers, but the complete honeycomb comes from the simultaneous intersection of all these layer families. That distinction completes the picture. The directions describe the organization. The lattice supplies the centers. The 24 cell supplies the local geometry. And the 16-cell honeycomb supplies the four-dimensional space-filling structure. So the remarkable result is not simply that there are 24 roots, or 12 directions, or a 24 cell, or a 16-cell honeycomb. The remarkable result is that all of these numbers and structures fit together exactly. What began as arithmetic has become geometry. What appeared to be a collection of points has become a lattice. What looked like a polytopa has become a local neighborhood. And what looked like 12 arbitrary directions has become a complete system of symmetric hyperplane families. This is the hidden order of D4, and it gives us a four-dimensional analog of the close-packed geometry we already understand in 3 dimensions. The three-dimensional story begins with 4 directions. The four-dimensional story requires 12. The cuboctahedron becomes the 24 cell, the ordinary lattice becomes D4, and the three-dimensional packing picture becomes a 16-cell honeycomb filling 4-dimensional space. So we can finally state the central idea of this chapter. The geometry of D4 is not hidden from the numbers. It is encoded by them. And once we learn how to read those numbers geometrically, the four-dimensional structure begins to reveal itself. The geometry of D4 is not hidden from the numbers. It is encoded by them. This is the geometry hidden in D4.